All right, I'll start by introducing the speaker. Maybe a couple more people will join. So welcome to this short Isogenies and Applications session. So we're going to have two talks. So the first talk is CSI-Otter, isogeny-based partially blind signatures from the class with action with twist. And this is work by Shu Katsumata, Yifu Lai, Jason DeGro, and Min Chin. And Shu is going to give the talk.
Thank you for the introduction. Yes, this is a joint work with Yifu and Jason and Lincoln. And I know this is an isogeny session, but I'm per se not an isogeny expert, so I'll try to make this as simple as possible. It's more on the blind signature side. Okay, can you touch the screen? Great. So yes, our result in short is that we construct the first Schnorr type 3-round blind signature based on isogenies. And well, this is the first blind signature from any isogeny assumptions. And basically, we're going to be using the C-side assumption. And also, it's provably secure for log concurrent sessions. And for the isogeny experts, we have a new hardness assumptions for these optimizations, which could be of an independent interest. So let me just dive into the background. So what are blind signatures? So it's just a fancy way of saying it's an interactive signing protocol with advanced form of privacies. So what we have is that we have a signer and a user, and the user is the only one that has this message right now. And they're going to have this interactive protocol. And at the very end, the user is going to obtain a signature on this message M. And what kind of privacy we have is that the signer will not know what kind of message this user had during this interaction. So looking from this transcript, it won't know what kind of message is signed. And obviously, it's a signature scheme, so we also want the normal notion of unforgeability, but a bit more complex because of this anonymity notion. And in this talk, the blindness part is the more important part, so I'll just explain a bit more into the more theoretical way of defining these stuff. So what we do is then, let's assume that the user, which is the challenger, has a random bit B, and it's going to interact with its adversarial signer. And it's going to sign two sessions with using different messages, MB and M1 minus B. So from the signer's point of view, it's going to view two transcripts T and T prime. And what blindness means is that after this transcripts are viewed by the signer and the user outputs two signatures, M0 and M1, it won't know which message came from which transcript. And when this holds, we call this scheme as blind. And this is the type of anonymity notion that blind signature provides. So very intuitively, what this whole notion is saying is that from the signature, you cannot trace back to the user that actually started this transcript. And this has been a very powerful kind of anonymity notion used in practice. So the very traditional applications were eCache, anonymous credentials, and e-voting. So people who know about uProof, this is what they were using internally. And it has found more recent applications, and I think this is why we have this more interest in it right now. So adding anonymity for cryptocurrency transactions, also hiding metadata in secure messaging, and also privacy preserving authentication tokens. So these are used, are based on these blind signatures or similar notions of this. And let me explain the more theoretical part. So how do we construct blind signatures? And at a very bird's eye view, we have two types of construction. The first one is a very classical blind Schnorr type. So this really stems back to Pointcheval-Stern 92. And this is very simple and efficient. So it's a very powerful paradigm. And it's based on a 3-round protocol. So when you hear 3-round, it's basically Sigma protocol. So it's based on a Sigma protocol. And the only thing is that when you do this very naively, it only secures up to a logarithmically concurrent sessions. So I won't get into this, but it's just a weaker form of unforgeability that you achieve. On the other hand, we have this Fischlin type, which is a more generic construction from standard tools like signature schemes, NIZK. So we have a generic construction from it. And yes, so we use it NIZK, and therefore, typically, if you do it very naively, we get it less efficiently compared to these Sigma protocol-based ones. But there are, several techniques to make it more efficient using very structured, the structure of the signature schemes and the underlying assumptions. And the good thing about this approach is that typically you get a 2-round protocol. So in some sense, it's round optimal. And you get these polynomially concurrent sessions for free because it's only 2 rounds. But this is like the 2 types of blind ways of constructing blind signatures. And in the classical group and lattices, we have we can instantiate both of this like using more standard assumptions or not like more well-known assumptions. And the thing is that when you think about isogenies, we don't have either of this yet. And for the first construction, the reason why we don't have this at a very intuitive level is that all the construction so far relies on this algebraic structure of modules or rings, while isogenies are known to be a bit weaker than that or less expressive than that. So we don't know how to really construct it. And when we go into this Fischlin regime, we actually have really no way of doing this because there is no efficient NIZK with a compatible signature scheme. And therefore, today's talk is going to be about solving the upper hand part and claiming that we actually can get blind signature from these limited algebraic structures, and we'll show you how to do that. And I think this is kind of it slightly deviates from the previous methods of constructing blind Schnorr. So I hope this will be a bit interesting. So let me review blind signatures. How do we construct this from classical assumptions? So as I said, the first step is having an interactive signing protocol. And this is going to be without blindness. And it's very easy. It's just a Schnorr identification protocol. So we just have this normal 3-round process. And the only difference between a Schnorr protocol is that, well, the user is going to be the one that has this message. So he is the one that's going to hash this message in the first round Y commitment into this hash and create this challenge C. So otherwise, this is just the Schnorr identification protocol. But obviously, this is not going to be a secure blind signature because it can't be blind because the signature contains the challenge and this response R. So the transcript really is connected to this signature. So the question is, how do we make this blind? So this brings us to the blind Schnorr protocol, which is that intuitively what happened is that, we had this C and R, the challenge and the response. And to blind that, what we would like to do is that we have 2 components. So we want to add 2 randomization factors, D and Z. So we just want to completely randomize this signature. But we can't do this for free because if you can do that, you will break unforgeability. So you have to be able to make it consistent with the user's view. And I'm going to explain how to do that. So first of all, from the signer's point of view, nothing can change because from the signer's point of view, it has to be blind. So we don't know what the user is doing. So from the signer's point of view, it's going to remain the same. But what the user is going to do is now it's going to sample this 2 randomness, D and Z, and it's going to just modify this first round commitment Y in a very particular way. So we're going to multiply G to the Z from the left-hand side and this H to D from the right-hand side, where H is the signer's public key right now. And the other thing is just the same. So, we're going to hash this C star using this Y star now. And since, as I said, we can't just provide a C star to the signer, it's going to subtract it with this D because eventually we want this C star to be C plus D. And it magically works. And this is really easy to check. So the original signature was satisfying this standard verification algorithm. But if you multiply G to the Z and H to the D from both hand side, what we get is that we get this equation, and this is just the randomized verification now. So this is how you construct blind Schnorr. And I won't get into the security proof and everything, but this is intuitively what happens, and it works. And when you think about this, this is a very simple idea, and you can get a modular construction for modules. So the core idea was that when you get this first round commitment Y, you randomize it in 2 different ways. And here we implicitly use the fact that this group G was a ZP module. I won't get into the details, but at a very layman's term, what I mean is that this commitment Y can be multiplied by 2 different types of elements. So we can multiply with the public key. And this kind of uses the power of like modules. And this idea has been very abstracted by these great work by Hawk et al., like 2 consecutive papers, and shows that there's a generic construction behind this blind Schnorr. And it's based on a linear identification protocol. And within that, it really uses this modular notion or this algebraic linear notion of the identification protocol. And therefore, it can be instantiated by classical groups and lattices, which has an underlying module structure to it. So that's the, I guess, the very basics of blind signatures. And now I want to get into our work. So how do we do that for isogenies is the question, right? So again, I'm not an isogeny expert, so all my co-authors are, but let me try to explain the very basics of isogenies. It's just that they're very simple in mathematical terms, they're group actions. And what it means is that you have this group that it acts on this set S and it will create a set element. So it sounds a bit scary, but what happens is that you have this group element and you have this multiple or this acting operation on a set element, and it creates a set element. So in isogeny terms, what it means is that G is the so-called class group, which is isomorphic to Zn and efficiently computable for these type parameters. And the S is the set of elliptic curves. So, you know, when you have these elliptic curve elements, you can't really operate them together. So this is how you view this. So let me just provide one example operation of this. So it's a group action. So once you have this, you know, set element H, you can multiply it again with this or act it with this group element, and you will just have this back. And for compatibility, you would have this, you could do the group operations first and then act it on the set element. So this will just be G to the A plus B acting on this elliptic curve E. So these types of operations you can do. And you can see that, you know, like you can multiply a lot of things from the left-hand side. But the most important thing about group action is that you have no operations over set elements. So you don't have these like weird notions like E times H now, because these are both elliptic curves that you can't do this operation right now. So to be a bit more, you know, like with context, so this E will serve as this base elliptic curve, which is the analogy in the classical group will be this group generator G. And this G to the A, I know it's like, you know, it's a similar font, but this is the fracture symbol. So it's a different G. So this G to the A in the terms of elliptic curves, I mean, in the isogeny world, will just be the exponent A in the classical setting. So these are the corresponding that you want to view if you are uncomfortable with this kind of notation. But it will be very easy, I think. So once we have this group action set up, it's very simple to have a base non-blind protocol based on isogenies or group actions. And unfortunately, due to like this very limited structure, we can't have a very strong form of a sigma protocol, but we can limit the challenge space to be 0, 1 and just rewrite everything. And I promise you this works. And this is one way to do sigma protocols from isogenies. And now the question is, how do we make this blind using this blind Schnorr idea? So in the module setting, let me say it again. So the reason why it worked was because you have this first flow commitment Y, and you had two ways of randomizing it. Unfortunately, in the group action setting, we don't have this privilege anymore, right? Because you have this first round commitment Y, which is just this set element. And this set element can only be operated in one way. So if you try to randomize this Y, well, one way to do it is just you act this group element G to the Z from the left-hand side. You can do this, but you still have one more operations that you have to do, which corresponds to this blue box, which is you have to operate with something with the public key to make this idea work. But the thing is, also the public key, you can only multiply with the left-hand side, and it doesn't really operate with Y and H. So if you have two elliptic curves, Y and H, you can't mix them together. And this is why you can only randomize it once, and the blind Schnorr idea failed in the isogeny setting. So I think this is why people didn't really look into this any further, because it seems it's very limited and you can't do anything about it. So this is where we, you know, the twist comes, I guess. So isogeny is actually just not a group action, but it has a slightly stronger structure than that. And it's that I think people, you know, even if you don't do isogenies, you might have heard of this quadratic twist. And this has been lately used in several constructions. And we also exploit that feature too. So given this H, this elliptic curve H, we can do one operation and we can take the quadratic twist of that, which is just a fancy way of saying you can well, okay, I think from the isogeny setting, it's for isogeny experts, this is a very maybe not a well-defined operation, but it's basically the inverse for people who don't know isogenies that much. So you could compute g to the inverse minus a times e. So in the classical setting, this is really the inverse operation. So if you have h equals g to the a, you can always compute h inverse g to the inverse a. And you could do this using the quadratic twist in the the isogeny setting. So now we have this one extra free randomness that we can use. And this is actually enough to construct blind signatures. So let's see how we do this. So we're going to rewrite the sigma protocol slightly differently now. So the challenge space was 0 and 1, but now we're going to make it 1 and minus 1. This is nothing novel, like this has been used in prior works. So we're going to have this sigma protocol where the challenge 1 minus 1. And so everything's going to look a lot more like the normal Schnorr identification protocol. It's just that this challenge is limited to 1 and minus 1. Now let's see how to make this blind. So the way we're going to make it blind is a bit more different though. So we had this c to the d, and in the Schnorr setting, we added 2 randomness. But now we're going to have this multiplicative notion because the challenge space is a multiplicative subgroup of z to the n. And we're going to randomize it by c times d. And for the other component, we're going to randomize it like this. And let us see, why this works now. So the goal is to create a signature that ends up like this. So let's see how it works. So again, this g to the z is simple. So we can always randomize it once from the left-hand side. And how do we randomize this other part, this blue box? We're just going to take it to the exponent of the d. So we're going to take the inverse or just remain it as it is. And this is the other randomization using the quadratic twist. So we now have 2 ways of randomizing it. And everything else remains really the same. And the question is, why does this work? And when you work out the details, it's really easy to see that it works. So the original scheme was this. You first multiply everything in the exponent by d. You take the quadratic twist of everybody. And then you add g to the z from the left-hand side. You acted on it. And then you get this randomized scheme. So it might look magical, but this is why it works. And this is why we have this a little bit of a weird randomization. That's just not an additive term anymore. But when you work out all the details in the secure proof, you can see that this actually is enough. So in other words, what we did was that this is not really limited to isogenies or anything. It's just that it's just another way to blind the Schnorr identification protocol. So in retrospect, the blind Schnorr was doing a very smart way of randomizing, which was just adding 2 things. And this really works because you have 2 different ways of operating on Y. So that's why you could do this. But you could actually do it in a different way, even for Schnorr. You could do this multiplicative blinding, and then you do some additive blinding. So there's actually a lot of different ways of blinding. So this is, in a bird's eye view, what we did, like re-observing blind Schnorr and making it work for isogenies. So I have a bit of time left to finally explain about partially blind signatures, because we have another kind of obstacle that we face for isogenies. So partially blind signature is where a signer and a user can use this one public, so they can agree on a common public message and then include that in the signature. And in practice, this is actually really important because you have to enforce some rules, or otherwise this user can sign on any message. So in practice, one way of using this common message is that you embed the expiration date of this signature where it gets revoked. And you really need this property. So when you actually want to deploy blind signatures, typically you want this partially blindness too. So for people, if this is the first time looking at partially blind signature, I think the strawman idea that you might think of is just, well, why can't you hash this common message into the signature? Because this is typically how you bind a message into a signature in normal signature schemes. But obviously it doesn't work because the blind signature scheme that we're trying to work on, and you can't really prove that you hash this correctly because we can't really show this to the signer. And the user might be actually putting in a different common message and it won't work. So this is why in 2000 in crypto, Abe Okamoto came up with this nice idea of constructing partially blind signature using these OR proofs. And what they do is that, this is the normal So in blind Schnorr, the signer was implicitly just proving knowledge of its public key. But what we're going to change is that we're going to first hash this common message M star into this H star. So we're going to hash to this point H star, and nobody's going to know this G to the A because it's produced by this random morph right now. So what this happens is that now the prover or the signer is going to prove that it knows a secret exponent of either its public key or this H star. And from the adversary's point of view, they can't do anything because obviously they don't know the secret key of H, or they don't know the secret key of this H star. So it still works as a normal blind signature, and it's also partially blind now because the signer is the one that can embed this H star into the signature now. So this is how it works. So a naive idea of doing this in the isogeny setting is that let's just hash this set of elliptic curves. Unfortunately, we can do this because isogenies don't have this property that you can hash into the elliptic curve. The only thing you can do is that hash into the G to the A and then construct the elliptic curve. So therefore, this idea doesn't work. And if you want to do this, well, you need to know the secret. So that's why it doesn't work. And the final key idea to kind of overcome this is that we can extend the OR proof into a 2 out of 3 proof. So what happens is that we're going to extend the Okamoto-Schnorr idea into 2 out of 3. So now the signer is going to have 2 public keys, H0, H1, and it's just going to discard one of them. And it's now going to prove knowledge of 2 out of 3 exponents, which is H to the 0, or it knows the exponent of H to the 1. And finally, or it knows the exponent of H star. And this H star is a random elliptic curve, but everybody's going to know this secret of this elliptic curve is because we're going to hash into the secret key and then create this elliptic curve H star. But the point is that the signer can still sign because it's always going to know at least 2 of the secret keys. But from the adversary points of view, it knows A star, but it won't know the other A0 or A1. And it looks a lot more complicating, but we can still work out all the ideas and make it blind using the previous idea that we shared. And we can also prove unforgeability, which is a bit more tricky, but still we can do this. So, right, sorry, I'm going a bit over time, right? So there's a lot of omitted details on the talk, so I won't get into detail, but for people who care about the more mathematical part, we do have these optimizations using higher degree roots of unity, which could be an independent interest in other applications. And finally, for people who know about the Ross problem, we initially thought this is going to be a very nice idea to work on because the Ross attack really uses this linear idea to break stuff, and isogenies doesn't have this. But we have this ongoing work that we can actually show a bit about this more fully concurrent setting. So people who are interested, we will have some results soon. So yeah, this is the result. Thank you for listening.
So are there any questions from the audience?
Thank you for the talk. I was wondering, the security problem your signature is relying on seems different from the one that's that has been worked on last year, but still a little bit close. So can you formalize what's the exact security problem you're based on?
Wait, can you say a security problem?
Yeah, I mean, is it like do you consider that you can't forge signature because you can't find isogeny between 2 elliptic curves, for example? I'm not exactly sure to see what you mean.
So we're using the CSI parameter, which is, as far as I know,
oh, so it's the exact same problem. Oh, okay. Okay, thank you.
Questions? Yeah, I just had a quick question, like whether, I mean, there are schemes in the discrete log setting that are resistant to ROS, but they all require ideal model proofs at this point, like AGM or generic group model. So do you think is there first of all a natural translation of these countermeasures, and second of all, do you expect maybe you can prove them in some, I don't know, modified generic group action model or something like that?
So that's a very great question. And as far as we checked, I don't think it's doable, but we can always, we could discuss this offline. Like, it's not an easy answer, I think.
Thanks. All right, so let's take the speaker again. And if the second speaker can set up.
Sorry.
All right, so when we finish setting up, let me introduce the second speaker. So the next talk is on weak instances of class group action-based cryptography via self-pairings. This is joint work by Ludwig Kastrik, Marc Houdin, Simon Felix-Merz, Marzio Mula, Sam Van Buren, and Federico Cadrea. And Marzio will be giving the talk.
Okay. Thank you for the presentation. Maybe lift it. Okay. Can you hear me? Okay. Okay. So the problem, I will start with the very basic problem of isogeny-based crypto, which is I'm not sure if I can control the slides. No. Yes. I will start with the very basic problem of isogeny-based crypto, which is given two elliptic curves over some finite fields to find a secret isogeny within them. And this is still unbroken. Throughout this talk, I will always assume that we know the degree of this secret isogeny. You can see it just as some integer attached to the isogeny, which is correlated with how large is the kernel of the isogeny. So we will also assume that the degree of the isogeny is smooth, meaning that it only has small prime factors. And what happened 1 year ago was that it was proven that if you are given some extra information, which is the images of two suitable points on the starting queue, then the crypto system is broken. You can perform the SIDH attack and recover the secret isogeny. Fortunately for us, not every isogeny-based crypto system uses this extra information, torsion information. And actually, yes, we also have a reduction, which tells us that you can actually just have the image of one suitable point in the starting queue, and then you can perform the SIDH attack to improve this. But as I was saying, this is not always the case. So for example, in C side, you don't have this extra information, but you just have the codomain of your secret isogeny. So our goal now is to try to fill this gap. So to find a way to recover the image of suitable point, which can then be used to perform SIDH. And this was kind of the motivation for our and in particular, we tried an approach that exploits the power of self-pairings in order to do that. Now, I will try to show you why self-pairings are so appealing to perform this attack. And the reason is the following. When you work with class group action-based crypto systems, you can always actually recover, well, not the image of P, but some multiple images. You don't know as an attacker which multiple it is, but you know that it is some lambda times the image. So the goal of an attacker will be to find this unknown sky. Okay, so in a dreamlike scenario, you could just use the vibe pairing. So what could you do? You take this unknown multiple lambda times phi of P, you perform the vibe pairing of this point with itself, and by the properties of the vibe pairing, this is the same as if you compute the vibe pairing on P with itself and raise it to the square of lambda times the degree of the result. As I was saying, we are assuming now that we know the degree of the secret result. If you could do that, you could just perform a discrete logarithm computation because the codomain of the vibe pairing is some finite field with some roots of unity in some finite field, so you can easily compute that and you recover that. Well, the problem is that the vibe pairing is symmetric, so if you compute it on a point and with itself, you just get one. And so there is no point in trying to recover any information from a discrete logarithm computation. So the question is, can we build some function that has a similar property as the file pairing, but which is non-trivial when you compute it on a point with itself? So before trying to answer this question, I will briefly recap how class group action-based cryptologic systems work. In the previous talk, we talked about CSI, but there are actually some ancestors of CSI that I want to mention, and also some variations of CSI, which are the target of our attack. So the basic idea behind class group action-based crypto system is the classic Diffie-Hellman key exchange. Of course, I will not go into the details of this quite common protocol, but the idea is that the secret is just some secret exponent to which you raise a given generator for some secret group X. And what was done in the 90s by Kovanian, Rostostev, and Stolberg, but was trying to generalize this to a more general setting and just use group action. And here you can see that the same scheme still holds if you just switch the notation to the notation of class group actions. So in this case, what they did was starting from some ordinary elliptic curve defined over some finite field. And in this case, you know that the endomorphism ring of the curve is isomorphic to some imaginary quadratic order, which you can just see as z with the square root of some negative integer. And then the scheme is exactly the same as before. So you sample some random secret element from the class group, and you let this secret element act on the starting curve. And then this gives you some isogeny, as I will show you in the next slide. And the codomain of the isogeny will be the action of the secret element over this group. Okay, so to give you a little bit more details, let's go back to the setting. So we start from, as I said, from an ordinary elliptic curve defined over some finite field, and its endomorphism ring is isomorphic to some imaginary quadratic order. Then the set you use for the protocol is the set of all elliptic curves over FQ, which are FQ isogenous to the starting curve, and whose endomorphism ring is the same as the endomorphism of the starting curve. And as I said, the group you use for this action is the class group corresponding to this imaginary quadratic. Okay, I'm not really interested in saying how the action works exactly, but it is enough to say that the action amounts to computing some isogeny starting from the starting curve, and the output of the action is indeed the codomain. And you can actually do that even if you start from a super singular elliptic curve, which is exactly the case for C-side. But there is a big difference because the endomorphism ring now is not anymore an imaginary quadratic curve. But yet you can somehow cut a slice of the endomorphism ring, which is again an imaginary quadratic curve. And the way in which you cut this slice is by means of so-called orientations. So you give some injective map going from some imaginary quadratic order inside the endomorphism ring of the given curve. In the case of supersingular elliptic curves over FP, this injection is particularly easy to compute because you just take the so-called Frobenius endomorphism, which is the spatial map sending the coordinates of a point to the same coordinates raised to the power, where P is the characteristic of the field on which you are working. And essentially the set you define here is the same. So you take all the curves defined over FP and which are connected with the starting curve via some FP isogeny. So some isogeny which is somehow compatible with the Frobenius endomorphism. And the action is exactly what's before. But actually to describe our attack, I want to stress that you have a lot of choice for your imaginary quadratic order. So you can go more general here and just say, okay, let's assume we start from some elliptic curve and that we have an injective homomorphism sending some imaginary quadratic order inside the endomorphism ring of this curve. And then you proceed exactly as before, with the only difference that now you have to consider the so-called O-oriented isogenies between the curves in the set. So you consider only the isogenies that are somehow compatible with the orientation you are considering. And this compatibility is actually also the thing that allows you to perform the attack as I described before. So the thing that ensures that you can always find some unknown multiple of the image of P you are looking for. Okay, so the bottom line is just that you have a lot of orders to choose when you build some crypto system based on class group action. But are there bad choices? And this is the question that motivated us. For sure, if D is very small, then the class group is going to be super small. And the class group is the set of secret keys. So you really don't want to choose a small value for it. But in our work, we showed something stronger, which is that these should not have small factors. And in particular, as a small, as power smooth quadratic squared factor is particularly bad for our attack. So as I promised, we will now define something that resembles the Weil pairing of a point with itself, but is slightly more general. So we will look for something that is non-trivial. So the two properties that I want to emphasize here are that if you apply a self-pairing to a multiple of a point, it is the same as if you apply the self-pairing to the point and raise it to the square of the scalar. And the second property I want to stress is colored in blue, and is this compatibility property. And I want to stress that this is exactly the compatibility we have for the Weil pairing. So if you compute the self-pairing on the image of a point, it is the same as if you compute the pairing of the starting point and raise it to the degree of the answer. Of course, for our purposes, we will not know what is the isogeny we want to have compatibility with. So we will have to overshoot it and have compatibility with all the oriented isogenies involved in the process. So let's go back to the attack idea I was describing at the beginning of the lecture. So we are just adapting the notation to this class group action notation. So, well, the isogeny simply arises from some secret element of the class group. And I stress again that we know the degree, and the degree is smooth. And so the idea of the attack, as I was saying, was using self-pairings that are compatible with all the oriented isogenies. And using that, our goal is to recover the image of some suitable point and then perform the SIDH. But let's make this arrow bigger and see in more detail how it works. So you start from some small prime, not dividing the degree of the isogeny, and you choose a good cyclic subgroup of the starting theorem, making sure that the order of this group is, well, square and is bigger than the isogeny you want to recover. And as I was saying, in this oriented setting, you can always find out what is the image of this group, even though you don't know exactly what is the image of the point generating this group. So you can get point P and lambda times the image of P. So this is exactly what I was describing before. And then you can exploit two self-pairings defined over these two groups, and which are compatible with all oriented isogenies connecting curves, in order to perform the same trick I was performing before with the Weil pairing, with the exception that now, if we have something that is non-trivial, we get exactly the scalar lambda we want. Okay, there are two problems here. The first problem is that these two pairings might not exist. So we might be in the situation where we are somehow forced to have the Weil pairing, or something trivial anyways. And the second problem, of course, is that even if these self-pairings exist, they might be not very easy to compute. So our main result addresses the first problem. So when do these suitable pairings exist? And well, the key property is emphasized in blue. So the order of this pairing, meaning that the magnitude of the image of this pairing, has to be a divisor of the discriminant of the order. And this already tells us that this attack doesn't work for society. And this is because the discriminant of the order in society is -4 times P. And P is not allowed. And if you look at these extra cases, 4 doesn't really give you any useful information. So we will shortly see which cases are really affected by it. So when these pairings exist, we have two different situations. The first one is the Frobenius-oriented situation, which somehow enables us to use Miller functions, which are used to compute the prior tape pairing. And this makes for a very fast attack. So polynomial time attack. While in the general case, so when you don't have the Frobenius orientation, things are more tricky because you need to move to larger field extensions. And this is due to the fact that actually the Miller functions are the only reliable way to compute efficiently some sort of pairing, and most pairings somehow arise from the Tate and Weil pairing. So in this case, you will need to move to a large extension of the field, which in the worst case is going to be extremely large and go for a sub-exponential attack. And in some cases, it will be still okay, but yet not as fast as the Frobenius case. So which are the protocols that are affected by this attack? Well, for sure, in the Frobenius-oriented case, as I was saying, and for the power smooth case, we have an attack which is efficient. Well, I actually cheated a little bit to simplify things. Our result holds even if you don't choose a prime element. You could just work with some smooth integral and look for groups whose order is to the 2 times r, or some r. And in this case, we have some partial result that says that for the Frobenius-oriented case, you still have an efficient attack. And actually, if you want to feel super safe, well, you just need to stick with discriminants with no small factors, because in that case, subpairings that don't even exist, so you cannot perform any attack, even if you find out some way to compute them efficiently. So to conclude, where the first question that is left open after our work is whether we can compute subpairings more efficiently in the non-Frobenius oriented case. And yeah, as I was saying, we can perform the attack even when working with just smooth L and not just a prime. And for this case, we still have a non super precise estimate for the attack time of the attack. Another interesting question is, well, I always said that we want to work with groups whose order is larger than the degree of the secret isogeny, but we could still recover some information for subgroups whose order is smaller than the degree of the secret isogeny. So it's interesting to see whether you can use this information somehow to recover something about the secret isogeny. And finally, in the full version of our article, there is another version of the theorem I was mentioning before, where you relax the compatibility condition. So you just ask compatibility with oriented isogenies whose degree is co-prime with them. And for this case, I mean, it doesn't change much because you get just a factor of 2 usually. But for this case, we don't have still an explicit construction. So it would be interesting to see whether there is such construction. And with this, I conclude my talk, and I thank you for your attention.
Right, thank you. So we have plenty of time for questions. So if you are on Zoom and you want to ask questions, feel free to type them in the chat. Ready? Right, so if there actually are no questions, so I think we can actually end this earlier. And there's actually a tracks switch break, so until 11:15, so you get a slightly longer break. Thank you.
Thank you.
Let's take back speaker again. Oh, wait. Okay.